Thank you, Dr. Takashima, for the introduction. Hi, everyone. So let's get started with our presentation. We have no COI to this presentation. Contents are here. Before introducing our study, I'd like to explain the basics. The mechanism of O17 water as negative contrast agent in proton MRI. O17 is one of the stable oxygen isotopes and has a spin quantum number of 5 halves. Therefore, protons in O17 water have 6 Raman frequencies, resulting in broadened peaks and very short T2. The proton T2 of O16 water nearby O17 water is also short due to chemical exchange between the protons. The natural abundance ratio of O17 is 0.04%. So in vivo, with a minimal background presence of O17 water, the presence of O17 enriched water can serve as a negative contrast agent. Then let's talk our study. This talk was already published in JMRI last year. Abnormal aqueous flow in the eye can increase intraocular pressure and cause diseases such as glaucoma. Therefore, visualization of the aqueous human flow could help diagnose glaucoma and determine the effectiveness of treatment. However, gadolinium, which is an MRI contrast agent, does not pass rapidly through the broad retinal or broad aqueous humor barriers of the capillaries, so the maximum contrast agent is several hours later. We hypothesize that after O17 water eye drops to the eye, a specific region of the eye with O17 water will have low signal intensity on T2 weighted images. Therefore, the purpose of our study was to observe the distribution of O17 water in the eye and its flow in the anterior chamber using dynamic T2 weighted MRI. Here is the anterior chamber region. This study was prospective. The final subjects were 6 normal volunteers. For MR data acquisition, a clinical 3D MR system was used. The 10% concentrated O17 water saline was applied via eye drops to the right eyes of all subjects. The sequence and parameters of dynamic T2 weighted proton MRI are provided here. There were 3 protocols for data acquisition. Here is the O17 water drop period of 1 minute. Not knowing how long imaging time was appropriate, the first 2 subjects had short imaging time of 12 minutes. Longer protocols had some eye closed period for subject to have a rest. During dynamic MRI, the subjects were asked to stare at a single cross point. This horizontal line of the cross point consisted of a white board with black edges, so that the subject's gaze was always parallel to the XY plane. This approach reduced movement in the pitch direction of the head. At post-processing, eye movements were also corrected using 2D nonlinear transformation, employing MATLAB Emmerich Demon's function. The pre-eye drop images were used as an alignment reference. These are some different images. After post-processing, any white and black edges that appear due to movement was corrected. The low signal intensity in the anterior chamber region suggested the presence of O70 water. As part of image exclusion criteria, images obtained during eye close period or images with significant motion artifacts were excluded from the analysis. The images with significant motion artifacts were identified using IQR method with reference to the left anterior chamber or left anterior vitreous body region. To investigate signal intensity of the images, two approaches were conducted. One was creating difference images, while other focused on calculating signal intensity time variations. In each difference image was obtained by subtracting the pre-eye drop images from the post-eye drop images. Signal intensity time variations were calculated in the right anterior chamber region. Its signal normalization was done by dividing the right anterior chamber ROI by left anterior chamber ROI. In difference images, a decrease in signal intensity after the eye drops were observed in anterior and posterior chambers, but not in the vitreous body. In both chambers, the most signal decreases were observed at 8 to 8.5 minutes after the eye drops. Here is an example of time variation of normalized signal intensity. The signal decreased after the eye drops, then back to recover, reaching a value close to before eye drops at 40 minutes. There was a linear relationship between the R2 change of the water protons and O17 water concentration. The time variations of O70 water concentration were calculated. Here is the time variation of O70 water concentration obtained from the same subject as the previous slide. Inflow and outflow constants were determined using different exponential equations, which are provided here. Table shows data for all subjects. The inflow constant of O70 water was significantly faster than the outflow. In summary, our study demonstrated that the feasibility of observing the distribution of O70 water eye drops in the anterior chamber using dynamic T2-weighted proton MRI. The inflow of eye drops into the anterior chamber was significantly faster than the outflow. Thanks to these grants and individuals for their help. Thank you for your attention.